Okay, hi all. Welcome to today's session. So I'm excited to introduce Stefanos, and I've had the pleasure of knowing him since his days pursuing his PhD at CMU, where he was collaborating on an NIH grant. And then before that, he was also a student at Cambridge over here. He was completing his master's at MIT, working with Professor Julie Shah. And he serves as an assistant professor of computer science at University of Southern California currently. And Stefanos is not only an accomplished scholar, but he's also a leading figure in the field of HRI. His contributions, particularly in modeling interactions between humans and robots, have been both significant and influential. And before we begin, I would just like to highlight a few housekeeping points. So first, I want to remind that everyone, we are recording this talk for future references. And secondly, kindly mute your microphones throughout the presentation. And in case if you have any questions at any moment in the talk, please utilize the raise hand feature on the Zoom. And finally, we have also allocated some time for discussions right after the talk. It will happen over on the same Zoom link. So I encourage you to actively participate in the discussion. So without further ado, please join me in welcoming Stefanos. And Stefanos, please take the stage.
Thank you very much, Sid, for the kind introduction. Can you all hear me okay? Okay, perfect. Yeah, thank you. Thank you for the introduction and also for the opportunity. Also happy to share that I'm no longer an assistant professor. So now my bio just changed a couple of days ago to associate with tenure. But it's a real pleasure to be presenting this work to MERL. And so what I'm going to talk to today is about enhancing the efficiency and robustness of human-robot interactions. And so there has been a lot of work, of robots working autonomously in factories, in the automotive industry, for example, where they do everything on a specific constrained environment. They do repeated tasks, and the humans are far away from the cage. But there are a lot of tasks that still require human dexterity and expertise. And there are a lot of tasks that require manual work. And one of these tasks is, for example, assembling a furniture or assembling a customized satellite. But even in this type of tasks, robots can still support human users by providing supporting tasks. So for example, robots can lift up a heavy load, and they can fetch parts to the user to improve efficiency and so on. And so what we would really like to have is we would like to have robots that are efficient in that they help improve the interaction. They help people do the things that they would do otherwise much faster, but also robust. So for robots to be deployed, they need to operate over long time scales without catastrophic failures. And so what I'm going to talk about today is I'm going to first highlight only the first thrust, which is how we can have efficient human-robot interactions, and then take a deep dive on the second thrust on robustness. So when it comes to efficiency in human-robot interaction, our thesis is that we can improve efficiency by adapting to human preferences. And what I mean by that is that in many, many tasks, users have their own individualized preference on how to perform a task. And so what this means is that, for example, a mechanic may choose their own specific way on how to place the screws, what sequence to place the screws, and how to drill them. But also there are physical ergonomic preferences. So people, for example, if they are to do this surface refinishing task in the bottom of the screen, then the way the robot should place the surface would depend on their height, their physical characteristics, and so on. And for robots to be efficient collaborators, they need to be able to adapt to the preference of the human worker. Now, one way to learn from preferences is through demonstrations. So what, for example, we could do if we want a robot to help people assemble an IKEA bookcase, would be to have people assemble a bookcase multiple times, and then the robot can learn how they prefer to assemble a bookcase. But this is really very tedious and time-consuming. And so the question then that we ask is, can we enable a robot to adapt to the preference of a human worker without demonstrations on the actual task by that worker? And the key insight that, well, the first answer that we gave was to exploit similarities between different workers to identify dominant preferences. So even though every one of us is different and we have our own preferences and biases, people tend to optimize for similar things. And so the insight here was that perhaps there are dominant preferences in, even if there is a near infinite ways of completing a task, perhaps there are some dominant preference that people can be grouped on, and that perhaps we can exploit these similarities for efficient inference. And so, for example, here, when we did a study and asked people to assemble a bookcase, we first, a lot of people first just placed all the boards together, they connected the boards, then started plugging in the shelves. Like this user here. On the other hand, another very, very common preference was that people first use the connectors to be the base, and then they use that as a base to put all the shelves later on. And we actually found out that for not everybody, but for a large majority of participants, they were grouped to two or one more. There is one more preference, but to three dominant preferences. And so the proposed method is that then, we can have users, a population of users demonstrate their preference. We can learn what the dominant preferences are through some unsupervised learning. And then when a new user comes, we can observe their actions, infer what the dominant preference is, and the robot then can proactively assist them. So the robot can observe their actions, associate what the user is doing with what the prior that the robot has on the human preference, and then proactively take supporting actions. And this is a demonstration of this work where the user starts building the connectors first, and then the robot quickly infers which cluster they belong to, and then proactively gives up the right tool or the right part. Now, this does not require the new user to provide demonstrations, but it does not really solve the problem because we still require access to demonstrations from a population of workers. And so let's say that now we change the task a little bit, that would require acquiring a completely new set of demonstrations. But one thing that we have observed in this bookcase assembly example is that participants often explain their preference using task-agnostic features. In other words, when we asked them why they chose to do specific actions in specific times, they said, "Oh, I wanted to leave the shelves towards the end because they are the heaviest and I didn't want to get tired." Or they said, "I wanted to connect the boards first because the connection is the mentally most challenging task and I want to get it done early." So they used features that are not specific to the task, but are more generally specific to the effort required to complete specific actions. And so what we did then is perform a study and asked ourselves, if we have users perform some type of a task and we have them choose their actions based on mental or physical effort, would this transfer to a completely different task? And so we we came up with a canonical assembly task, which is a short expressive task that allows people to choose between actions of different workload. And then we had them do the actual assembly task. And so this is an example where users will start with actions of high mental effort. So this participant here actually could choose between actions of high or low mental effort, but selected actions of high mental effort first. And the purpose of this task here is just to observe what type of actions people will prioritize. So the mental effort action here is to insert a wire, right? And then they will do the lower mental effort action of inserting the screw. Now the question is, what if we have the same user without telling them anything, do a completely different task? And we saw that for a very large number of participants, that prioritization was the same. So here in this airplane assembly task, the user started with actions of high mental effort first. So in this case, assembling the propeller. And then moved to actions of low mental effort, which was connect to the fuselage. And so the idea then is, if that's the case, then instead of obtaining demonstrations on the actual task that can be long and time consuming, why not obtain demonstrations first from a small canonical task that is a short expressive task, and then we can learn the preference in the form of the weights of a reward function, which, for example, inverse reinforcement learning, and then use these weights as a is preference of the user in the actual task. And then without any demonstrations on the actual task, the robot can actually go ahead and assist them. Now, in a perfect world, that would work great. The world is not perfect, and sometimes people would change the preference from one task to the next, or sometimes they would change the preference during the task. But what we really found is that it was very useful to have this preference weights learned from the canonical task as a prior. And then if the user changes the preference or there is any change observed in the actual task, then we can update that estimate. But compared to starting, for example, with a uniform prior or with a random prior or anything that does not have any information about how users prioritize their actions, we found that transferring the weights from the source canonical task and having that as a prior model significantly improve prediction accuracy. And so the idea here is that you can observe user demonstrations in some short canonical task that allows people to choose between actions of different workloads. You learn the preference in terms of like how they prioritize actions. And then in the actual task, you can actually go and directly start anticipating their action. And then if they make a change, you can update the model, make some correction on the model, and then proactively assist them and significantly improve performance. I see a raised hand, so yes.
Hi, Stefanos. Actually, can you go into a bit more detail on how you define a physical effort and mental effort, and what makes it high and low?
Yeah, definitely. So, right. So, well, here what happens is that different users may have different perceptions of what is high mental effort and what is low mental effort. And so what we did is we presented the task in the beginning and had users rate their perceived effort required for every action. And that was the feature. And we did it both for source and canonical task. And that was the feature that we used to specify what actions have high and physical mental effort. And then what we learned from demonstrations were the weights that indicate the importance of these features, right? But the features were essentially manually specified, and they were different for every user. So some users, so we described them in the task, and some users had different perceptions of what's high physical and high mental.
Nice. Got it. Thanks.
We also saw a decrease in human idle time. And what we are currently working on is how we can have a robot assist users in an airplane assembly task. And so the idea here is that, but here the idea is not just have static robotic arms, but also have a mobile manipulator, and how we can have the user, both the arm and the mobile manipulator provide supporting actions, and how this improves efficiency. Now, in these systems, improving efficiency is important. But I think if we want this system to be actually deployed, the robustness is an even more important feature, because even if the system is efficient, if occasionally it fails and fails catastrophically, then people are not being willing to adopt it. And so the second thrust that I'm going to speak in much more detail is how we can improve the robustness of human-robot interactions. And our approach is actually to generate diverse scenarios in simulation to try to find failures. And we'll have as example here this workspace collaboration task where the user goes towards a goal and the robot goes to a different goal object. And the idea here is that the robot uses the observations of the human hand as a way to infer the user's goal, and then does Bayesian inference. And then the idea is that the robot should try to go to a different goal. So the robot runs a partially observable Markov decision process with some approximations, but it tries to infer what the user's goal is and go to a different goal so that they coordinate efficiently and they don't manipulate the same goal at the same time. And so the user is like signing, the robot is labeling, and it's a collaborative task. And so the question here is, can we actually try to find failures in that system? So we tested the system extensively. It works very well. Can we adversarially try to find scenarios to change the scene or change the user behavior that result in system failures? And one approach would be to formulate this problem as a single objective optimization problem. But typically, a single objective optimizers what they would do is they would find a global optimum, which in this case would be, for example, the user being adversarial or putting the objects outside of robot's reach. But these scenarios are easy to find and they are not so interesting. I think what we are interested in is scenarios that the scene is cluttered, but also scenarios that the objects are far away. Scenarios where the user is adversarial, but also scenarios where the user is cooperative and optimal with respect to some reward function. So what we really want is a diverse range of challenging scenarios. And that drove us to go into the literature of quality diversity. And quality diversity algorithms are evolutionary algorithms that do not return a single solution, a single global optimum, but return a diverse range of high-quality solutions. So here you see the output of a quality diversity algorithm, where the idea here is that to generate images using a GAN, a generative adversarial network, where the quality is for each image to look like digitate. But we don't just want a single image that looks like digitate. We want images that are diverse with respect to, let's say, lightness and boldness. And so the output of the algorithm is actually a collection of solutions that each one of these solutions tries to be as close to digitate as possible, but also are diverse with respect to measures of interest, like how lightness and boldness. And so similarly, what we will do is we will try to find scenarios that are high quality in that they are challenging. In other words, scenarios that minimize systems performance, but that are diverse with respect to measures of interest, like distance between objects, rationality of the human user, and so on. And the goal here is to try to find failures. The goal is to try to find scenarios where the system fails to test the system's robustness. And so formally, the quality diversity problem assumes some objective function and some measures of diversity that form a measure space. And the quality diversity objective is that what we really want to find is a collection of solutions. So we want to find a collection of solutions theta for every output combination, so that every solution belongs to an output combination of a measure function. The measures are what we want to diversify, right? Measures of diversity. But also we want the quality of that solution to be as high as possible. So we want to cover that measure space with solutions, but also we want the quality of the solutions to be high. Now here, measure space is continuous, so we would need infinite memory to cover that. And so what many quality diversity algorithms do is they tessellate the space into a number of cells. And then what we try to do is we try to fill in every cell. So we partition the space, we discretize the space to cells. And for every cell, we want to find the solution so that every solution occupies a unique cell and the quality of the solutions is as high as possible. And we want to maximize the number of cells covered, but also the quality of the solutions that cover these cells. And so our insight here is to formulate the scenario generation problem as a quality diversity problem. And so the framework that we will propose is, first, we will search for diverse scenarios with a quality diversity algorithm. We will search, whereas a scenario here is scenario parameters. So for example, object positions or some parameters of the human model. And then we will pass those to a generative model to instantiate the scenario, to generate a scene. We will evaluate the scenario by simulating human actions and also robot actions, all that in simulation. And then we will evaluate with respect to how challenging the scenario is, but how diverse it is with respect to measures of diversity. And then we will return an archive of scenarios, a collection of scenarios, where here every cell in the archive is a different scenario. The archive, if it's two-dimensional in this example, it has two measures of diversity, and we iteratively do that to populate the archive. And so in this talk, I will start, in this part of the talk, I'll start describing every component of the framework. So when it comes to the search algorithm, a very popular algorithm is map-elites, where the idea behind map-elites is you search a high-dimensional search space of scenario parameters, you map them to a lower-dimensional measure space. This is a low-dimensional space that you want to cover. And every cell on that space corresponds to a different scenario, and you want to fill in these cells with scenarios, but you also want the scenarios to be as high as possible. And so the idea behind map-elites is that you first sample solutions from a fixed distribution, and then you select uniformly solutions from the archive. You perturb them with some isotropic noise, so you apply some random perturbation. And then you generate new solutions. And then if the new solution finds an empty cell in the archive, so it's mapped to a new cell, and if that cell is empty, you add it to the archive. If that cell is already occupied by an existing solution, then you compare the quality of the new solution with the previous solution, and then you add it to the archive if it's better. So in other words, you build an archive with elites, right? That's why it's called map elites, with the best performing solutions. And the key idea here is that existing solutions can act as stepping stones. So if you have a high-performing solution in some part of the archive, then if you perturb it, you're likely going to generate a new high-performing solution in some other part of the archive. So that's the state-of-the-art algorithm, MapElits. But one thing that MapElits does is it doesn't have any bias and it generates solutions with some perturbation. But can we instead generate solutions in the direction of maximizing the quality diversity objective? And so here, the quality diversity objective is to maximize the sum of qualities of solutions, right, in all cells. So can we generate solutions in order to populate the archive with elites? And here, let me clarify some terminology. The quality diversity objective is the sum of qualities of all solutions. And here I use interchangeably the word quality and objective to indicate how good every solution is. So a solution has some quality or some objective for that specific fault solution. And the quality diversity objective is the sum of qualities of all occupied cells in the archive. So this is what we try to do, right? We try to find a collection of high quality solutions. And so let's to generate solutions in the direction of maximizing the QD objective, we need to understand what happens every time we add a new solution to the archive. So the value of the quality diversity objective, which is the quality diversity objective score, is the sum of qualities of all solutions that occupy the archive, as we have said. Every time we add a new solution, we map it. We use measures to map it to a cell in the archive, and we compare the quality of the new solution theta prime to theta p to the current occupant. And if it's higher, then we replace theta p with theta prime. And so what happens then to the quality diversity objective score is it increases, and it increases based on the difference of the new solution versus the quality of the new solution compared to the quality of the occupant. Now, if the archive is empty, like if that cell is empty, so if the solution theta prime is mapped to an empty cell, then we assume the quality here to be 0. And so our approach here and our insight is to search explicitly for theta prime for that new solution in order to maximize archive improvement. And for that, we use the single objective optimizer named CMAES that models search directions with a multivariate Gaussian, sample solutions from that Gaussian, then selects and ranks them based on some objective. Here, the objective is fitness. But instead of selecting and ranking them based on some objective, we select and rank them based on archive improvement, based on how much they improve the archive. And then we update the Gaussian. And CMAES has also some step size adaptation properties, and it has also been shown that approximates the natural gradient of the objective that tries to maximize. So here we try to maximize the quality diversity score. So essentially we follow a natural gradient of the quality diversity objective. And if we combine CMAES with MapElits, we end up with a new algorithm named CMAME, covariance matrix adaptation MapElits, that had superior performance. And not only that, but here we have not assumed any access to the objective F, to the quality F and measures of diversity M. But if we have access to the exact gradients, then we can actually navigate this lower dimensional objective gradient space. And so we proposed a new algorithm named CMA Mega that leverages gradient arborescence to further improve performance. And so these advances help us search the vast continuous space of scenarios, of scenario parameters, because scenarios are very multidimensional. They have like a large number of parameters. Parameters are real numbers, often in case they're positions of objects and so on. So we need powerful algorithms to search them. The next component of this talk is how to generate scenarios. And here the insight is that what we can actually do is we can define a scenario parameters, the latent vectors of some generative model. And the benefit of that is that then if the generative model is trained with some human authored examples, and then we search the latent space of the generative model, we can actually generate scenarios that match the style of a training distribution of the human authored examples. And so here what we try to do is we trained a gun with levels. We started with video game levels of Mario, and then we wanted to search for scenarios that are diverse, but also challenging. So this is an example scenario where the Mario which runs an A-star algorithm on the level, finishes the task very quickly. But our goal is to search for adversarial scenarios. So for example, here we can generate automatically a level that results in the Mario getting into this type of infinite loop and never finishes. Now, we can also do this for reinforcement learning agents. So we did this for a state-of-the-art reinforcement learning agent that, again, so this is an agent that has partial observability. And again, we were able to find adversarial levels that result in this agent of getting into this type of infinite loop. But I'm more interested in human AI coordination and human robot coordination. So we took the overcooked game domain, and then we wanted to find levels that result in diverse coordination behaviors. So levels where the two agents coordinate very well, but also levels where the two agents get confused. So here you see the archive of layouts. Every cell is a different layout. And then one measure of diversity was amount of concurrent motion. So the higher, the better the coordination. And also amount of time stack. So the lower, the better of coordination. So as we go to top left, we have levels that result in better coordination. As we go to bottom right, we have levels that result in worse coordination, as evaluated by the amount of time stack and the amount of time that the two agents move concurrently. And we see that in the top level here, the objects are far apart and the two agents complete. Here, we fix the policy of the two agents and we just search for levels. And so the two agents complete the task very quickly. And the goal here is to efficiently finish and prepare a meal as fast as possible. But here we see a level where there is a long corridor. The two agents get a bit confused in the crossing. Now this agent has to wait for the other agent to come in. And there is a small amount of concurrent motion, and also sometimes the agents get stuck as well. And we see that this level here has actually long corridor. And it has also like a crossing. But also the two agents get confused. And also like they get confused in the crossing. But there was nothing in the optimization method that told the agents that there is actually a long corridor or a crossing. But this emerged out of the optimization process for searching for levels. Okay. So that describes the scenario generation process. In the next part, we are going to focus on how we can evaluate these scenarios efficiently. And so when it comes to evaluations based on evaluations, let's say on a sequential task where you have a robot and a human interacting with each other, then you need to simulate the task for a very long time, and evaluations can be quite time consuming. And so especially if you have like stochastic policies, stochastic robot policies, stochastic human policies, and also you have stochastic environment, then you need a lot of trials to perform the evaluation. And so the question is, can we speed up the process? And one approach could be to use deep neural networks to evaluate the algorithm, but evaluations in deep neural networks are cheap. So what this means is that we can very efficiently approximate the outcome, right? Instead of doing all the full simulation on a robotic simulation or in game engine, we can efficiently approximate the outcome with a neural network through a forward pass. But neural networks require diverse training data. On the other hand, quality diversity algorithms are ideal to generating this diverse data. And our approach is to combine the two. So what we can do is we can have a quality diversity algorithm exploit the deep neural network and generate solutions with a deep neural network. And these predictions of the deep neural network are going to be inaccurate, but the solutions generated are going to be diverse with respect to the network's own predictions. But what we can then do is we can take these solutions, evaluate them in the ground truth engine on the robotic simulation, and then feed them back to the deep neural network. And so in a way, what happens is the deep neural network learns to improve over time. just by correcting its own mistakes, right? Because we use the quality diversity algorithm to generate solutions. The solutions are diverse with respect to the network's predictions. We label them and we feed them back. And if we do that, we can actually significantly improve evaluation efficiency. So that's the scenario, how we can improve the efficiency of scenario evaluation. The last part of the framework is how we can update the archive. And right now, the way the archive is updated is we use map elites and combine it with CMAES and have the CMAME algorithm. And both map elites and CMAME generate solutions that are added to the archive if their quality is higher than existing occupants. And so what this happens, we have this elitist archive update where we generate a new solution, we map it through measures to a cell in the archive, and we compare the quality of the new solution to the quality of the occupant. And then if that quality is higher, then we replace the current occupant with a new solution. But we have found out that this type of update results in the following limitations for CMAME algorithm, for the algorithm that we have proposed. So one limitation is that CMAME struggles on hard to optimize objectives. A hard to optimize objective is an objective that is challenging to increase F, right? To find solutions of high F value, high quality. Now, why this is happening? Well, the way new solutions, we are searching for new solutions is we actually use CMAES to generate solutions and then evaluate them based on the improvement of the quality diversity objective score. And the improvement is the difference between the quality of the current solution versus the quality of the current occupant of the cell that the new solution is mapped to. But if the quality of the occupant, if the cell is empty, then the quality of that occupant is 0. And therefore, it's always easier to find solutions that occupy new cells than improving upon existing cells. And so in other words, there is an inherent bias that pushes CMAME to expand the archive and try to fill in the archive, as opposed to improving the quality of existing solutions in the archive. The second limitation is that CMAME struggles on flat objectives. A flat objective is an objective where every solution is a region where in the search space where every solution has the same value. That is important in scenario search because a lot of scenarios actually may result in failure, and then a failure is a failure, so all of them will have the same quality, and therefore CMAME will get stuck. And the last is that when the archive has low resolution, CMAME again has poor performance. So can we improve upon these limitations? And if we look at the first limitation, what we can do is we can define an annealing function. We can define a function FA that takes as input the new solution theta prime and is equal to the quality of the solution in the cell that theta prime is mapped to. So remember, theta prime is mapped to a cell in the archive with some measures of diversity. And then we can compare the quality of theta prime with the quality of the current occupant. And the elitist update, what it does is if the new solution has higher quality, then we replace the occupant. But instead of doing that, we can define F theta prime, FA theta prime, with some threshold. And every time we find a solution that is better than that threshold, we gradually anneal that threshold with the learning rate. So instead of just jumping and replacing the threshold with a new solution, we gradually change the threshold. Now, if the learning rate alpha is 1, then we have an elitist archive, meaning that we are back to CMAME and the previous updating mechanism, where we just replace it with a new solution. If alpha equals 0, then the threshold is constant and the archive does not matter. So in this case, we only care about the quality of solutions. We don't care about filling in the archive at all. And what we can actually show is that by smoothly interpolating between alpha equals 0 and alpha equals 1, we can move from CMAES. So if alpha equals 0, the algorithm will behave like a single objective optimizer because it ignores the archive. So we move like CMAES. So we only care about quality of solutions. And alpha equals 1, as we saw, results in CMAME. And anything in between is a smooth interpolation between single objective optimizations and quality diversity optimization like CMAME. And therefore, by introducing this annealing rate, we come up with a new algorithm named covariance matrix adaptation annealing elites. And what happens then is that if there is an objective that is hard to optimize, we can decrease that learning rate and make the algorithm behave less, bias less exploration of the archive, and more try to optimize for high-performing solutions, try to improve the objective. So that addresses the first limitation. Now, the second limitation is that CMME struggles on flat objectives. And what is a flat objective is that regions where all solutions have the same value, let's say 1. And what happens then is that every time we find new solutions, they all have the same value. So then we cannot rank them, and then the algorithm will fail. But what we would really like to have in a flat objective is we would like to have some type of frequency count where we keep track of how many times we visited every cell in the archive. And then what we would like to do is find the frontier where there are cells that are harder to visit, like the cell with the value 2 here, and visit those cells and try to expand those to populate the archive. Because if the objective is constant, then what we really care about is filling in the archive. So what we would really like to do is we would like to keep track of visitation frequency and descended density histogram. Now, the question then is how we can combine density descent and CMMA, the algorithm that we have proposed, with a learning rate. And the answer is do nothing, because actually what happens is that the threshold that we update with a learning rate every time we visit a solution becomes proportional to visitation frequency counts for constant objective. And so we can actually show that CMMA, this algorithm that introduces this soft archive, this archiving update with a learning rate and density descent are equivalent. And we can actually show that this results in much better performance. And the final limitation that we can address is that CMME has poor performance when the archive is low resolution. Now, I'm not going to go into detail, but we can actually show that with a learning rate, by adjusting the learning rate, we can change how fast the archive is changing, and that can affect the performance, that can improve the performance of the algorithm. So even though the archive is low resolution and changes very, very quickly, which makes CMME fail, by adapting the learning rate, we can achieve behavior equivalent to an archive of higher resolution, and therefore not have this detriment in performance. And so the key takeaway here is that just by adding this learning rate in how and thresholding mechanism on how the archive is changing, we can introduce a new algorithm that addresses all limitations. And so this concludes the final component of the framework that shows how we can populate the archive efficiently with scenarios. And so to summarize what I have discussed, I talked about CMME, CMA Mega. These are quality diversity algorithms that are ideal in searching the continuous space of scenarios. I talked about generative models to instantiate the scenarios, surrogate models like deep neural networks that can approximate evaluation outcomes instead of having to do this very long and time-consuming evaluation of scenarios to speed up the search, and an annealing mechanism, this thresholding mechanism that helps with improving the archive of scenarios. And so if we just use the quality diversity algorithms and generative models and the annealing mechanism, we can generate diverse images. So we can actually generate, we can have as objective to generate images that look like Tom Cruise, but as much as possible, but are diverse with respect to hair length and age. So as you go to the right, Tom Cruise gets older. As you go up, his hair becomes longer. And so this is an example collage of a single run of quality diversity search. And then you can put your favorite celebrity, you can put Jennifer Lopez, and you get a similar result. But what we really care about is robotics and human-robot interaction. So if we put everything together that I have discussed, we can actually generate the diverse failure scenarios for the shared workspace collaboration task. And so here a scenario is a position of objects, and what we can try to do is find positions where performance degrades significantly. And so here what we are going to do is we are going to search for object positions. We are going to repair. We are going to constrain these object positions so that they satisfy some boundary constraints with a mixed integer program. So in other words, we want all the objects generated to be within robot's reach. We simulate the human and robot in that case. we extract some system performance and measures of diversity for every scenario. We update the archive, and we do this iteratively. And not only that, but we will actually use a deep neural network to predict the performance and measures, to predict how challenging every scenario is, but also predict how diverse a scenario is with respect to measures of diversity, and populate this and find diverse scenarios. And if we do that, we can find some interesting failures. So this is an example where the human tries to reach one goal, the robot tries to reach to another goal but gets confused. The robot replants and tries to reach the third goal instead. And then the human tries to reach the second goal. And so just as to understand, there you see these numbers here that are probabilities of the human goal based on observations of the human hand that the robot is doing Bayesian inference. But then the robot that is running the human-aware planner is slow because the human is moving very fast. It's slow to understand which goal the human is going to. And so the result, when it finally understands where the human is going to that goal, it tries to reach to G1, it reaches some joint cleaning, it has to replan. And overall, the time to task completion, which is a performance metric that we use, is much, much longer, much larger than that of a nominal arrangement. And we can find diverse types of failures. So we can find failures because of incorrect call inference, failures because of self-collision, failures because of how the human and the robot order the sequence of goals, and so on. But I think what is very interesting with quality diversity algorithms is that they can give us a heat map. This archive of scenarios is a heat map that allows us to draw some qualitative inferences. And so this is a performance of our algorithm, deep surrogate-assisted generation of scenarios, compared to, let's say, map elites, or compared to random search, where we uniformly sample scenarios. And every cell here is a scenario, and yellow color indicates failure. So their team failed to complete the task in this domain. One measure of diversity in the top left is human variation, so how much the human deviates from optimal actions. The other measure is distance between goals, so how far away the goals are with each other. And from the heat map here, we observe two things. So first, we observe that if objects are far apart enough, then we cannot find actually a scenario with yellow color, so we cannot find failure. And that makes sense because if the objects are too far, then the robot can disambiguate in time what the human goal is and go to a different goal. But what is very interesting also is that even if the human is near optimal, so you see here the human variation, even if it's very, very low, that is like an optimal user, we can still find some failures. And so we can get this type of qualitative insights about the behavior of a system that we could not get with just running the baseline algorithm map elites, or by uniformly sampling objects. And what we are currently very interested in is expanding that that scenario search to more complex systems. So here and not only that, but so what we are interested in is first how we can generate different types of contingencies procedurally, right? Find scenarios that result in failure, but also, and then how we can have ways to address these contingencies. And especially we are very interested in rare contingencies, right? So something that would be completely unexpected and then occurs in a factory floor. And therefore, then if that happens during the actual testing, then the robot can go through some contingency recovery strategy to address that. And so this is a work in collaboration with Professor S.K. Gupta at the Center of Advanced Manufacturing. Now, one interesting application is that we try to find failures, but what we flip the sign in the objective, and we instead try to find scenarios where the team performs very, very well. And so we did that for warehouse layouts, where we tried to find layouts that maximize performance of hundreds of agents. And so on the left side, you see a human-designed layout that is very nice and symmetric. And then you see the agents running some pathfinding algorithm, but you see that like eventually there is a lot of congestion. Whereas on the right side, there is some weird layout that looks like nothing like a human layout, but then the agents coordinate very efficiently. And you can actually observe that when as we increase the number of agents or the number of robots, the human designed layout at some point, because of congestion, the throughput completely collapses. Whilst for our optimized layout, we can afford a much larger number of robots. And that's work in collaboration with Professor Zhao Yang Li at CMU. Now, all the algorithms that I have discussed are used in our open source library, PyRips. It has a lot of tutorials. It's used by multiple labs around the world, including Google DeepMind, Meta, Autodesk, and so on. So if you're interested, I would encourage you to check out the library. And we are also happy that the academic community has really expanded on and used our work on CMA-based QD algorithms. So they have used it to evolve diverse robot morphologies, diverse floor plans, diverse soccer scenarios for multi-agent systems, and so on. And so we have introduced this new class of quality diversity algorithms that formulate the quality diversity problem as an optimization problem and use single objective optimizers and adaptive optimizers like CMAS to search efficiently for solutions. And finally, one very interesting aspect is that the very same algorithms that we use to search for scenario parameters, we can actually also use them for neural evolution. In other words, we can use them to search for robot policies. So we can use the same algorithms where instead of parameters of scenarios, we search for weights of deep neural network that represent robot policies. And so we can find diverse walking gaits. So this is different types of gaits with but also we can find diverse walking gaits for a high-dimensional humanoid robot. So here we can find different types of gaits like galloping, walking, injured, and so on. And this work is in collaboration with Professor Gaurav Sukatme at USC. Okay, so to summarize, I talked briefly about how we can improve the efficiency of human-robot interaction scenarios, or of human-robot interactions by adapting to human preferences. But then I talked more in detail about how we can improve the robustness of human-robot interactions by generating diverse scenarios in simulation. And all this work was done to my wonderful students, by my wonderful students, but also I'm very thankful to my collaborators. And with that, I'd be happy to take any questions.